So let's look at number 6 on our assignment sheet. Let me see if I can move this out of the way. Okay, we have consider a buffer solution created by 500 milliliters of a 0.1 molar hydrocyanic acid solution and 2 grams of sodium cyanide. Okay, so look at the sodium cyanide. Which piece do we really care about in that sodium? CN. So when you see that, mark out the spectator. You don't care about that spectator. Go ahead and put your charge on your anion. And then we're making a buffer out of this solution. So we've got 500 milligrams of a 0.1 molar hydrocyanic acid solution. And I bet somewhere along the way we have a Ka for this. Now, Alex, did you find, Alex Le Guin, did you find a Ka value for HCN so I don't have to flip back a couple of pages? 6.2 times 10 to the negative 10th. Okay. All right, first things first, we need to get everything into moles or millimoles, okay? So I'm going to go ahead and convert this into moles because grams into moles is actually the fastest thing. Move your decimal point over 3 spaces to the left and then just multiply. So 0.5 times 0.1, and that should give you 0.05 moles. So you've got that many moles of the acid, and then we need to convert the 2 grams of sodium cyanide. And when you do your molar mass, you do have to do everything that's in there. So the sodium, the carbon, and the nitrogen, because you put in sodium cyanide into your container. All right, so 2 grams of NaCN. And I'm going to let you guys come up with a molar mass on that real quickly. There's 45?
You just said come up.
Well, I mean, correct molar mass.
22 plus 23. Oh my gosh. I don't want to get this wrong, but
I got 51 for the mass.
I got that wrong. Oh wait,
51?
No.
I got 36.
Hold on.
Oh, never mind. My bad.
0064.
All right, so let's try this again. I can't. Never mind.
Is that
49. 49. Who got 49? 49.01. I agree. Okay. All right, so do your math real quick. It's going to be a much smaller amount of moles. September, what'd you get? It's going to be a small number.
0.041.
Okay, good. Okay, so we have, now I know that it's moles of sodium cyanide, but again, we don't care about the sodium anymore because once we figured out how many moles of sodium cyanide we have, looking at the ratio of sodium to cyanide, that's a 1-to-1 mole ratio, so you would have 0.041 moles of cyanide ions. 49.01. We had 23 from the sodium. Okay, we had 12 from the carbon and 14 from the nitrogen. And it's actually 12.01, 14.01. Yeah, 22.9898. Yeah, gotcha.
Okay.
You good now? Okay, so now we're calculating pH. So let's use our Henderson-Hasselbalch equation. pH is equal to the pKa. So I want you guys to go ahead and take the negative log of the Ka value real quickly. And Tamari, if you would, when you get that, would you tell me that number that you get? I'm just going to round that to 9.21. That'd be okay. All right, and then plus the log of, is it base over acid or acid over base? Base over acid. So our base is the cyanide ion, so 0.041 over 0.05. Okay. And that will give you your pH.
So the base is HCN.
No, the acid is HCN. It's base on top of acid.
Oh, no, I was looking at that wrong. All right.
So 9.12, okay, it's our pH. Which if you think about it, we had more acid than we did base, right? So our pH should be a little lower than it would be if we just had all acid in there, okay? All right, let's look at the next part. It says, what volume of 0.5 molar HCl could be added to this solution before the buffering capacity ended? Now, what are we adding? Is that an acid or a base?
Acid.
That's an acid. And so what takes care of that acid? Which part of the buffer system? The base takes care of it. Okay, so you have to look and see how much base did we have? Well, we had 0.041 moles. When all of that is gone, your buffering capacity for the acid component is done. You can't buffer an acid anymore when all that's gone. So that's how many moles, the 0.041 moles we would have to use up to get to the point where we no longer have a buffer, okay? So if we know that's how many moles that it's gonna take to use up, and we know that we have this concentration of acid going in, couldn't you just multiply moles? No, wait. Molarity is equal to moles over liters, right? So what would I need to do to find volume? Would I multiply? Let's rearrange this equation. We would divide, there we go, divide by the molarity, because molarity and volume could swap out places. And so I'm going to take my moles and divide by my molarity, and that would give us how much volume we need to add in liters. You're right. Okay, and that's how much we would need to add in liters to end the buffering capacity for that buffer. All right, now the next part says what mass of sodium hydroxide could be added to this solution before the buffering capacity ended. Again, think about sodium hydroxide. It's a base, right? And so what takes care of that base?
Yeah.
The acid. So how many moles of acid do we have to take care of it?
0.05.
0.05 moles. Okay, and so we want to know what mass of sodium hydroxide. Let's just convert that to grams. For every 1 mole of sodium hydroxide, no, we didn't have the molar mass. I was thinking we did, but I did this one earlier in my first period class. So sodium hydroxide, y'all find that molar mass real quickly. And that'll be how much we could add to end the buffering capacity from the base end. And what are you getting for the molar mass of sodium hydroxide? Jasmine, what do you have for the molar mass of sodium hydroxide? 40, I agree. Okay. I'll call that 40.01, I think, from that. Okay, and then we're just going to multiply across. And what did you get as your grams of sodium hydroxide? 2.00 even. All right, we'll take it.
Wow, 2.0005, but that rounds up.
Gotcha. But how many sig figs were we originally working with? We're actually only working with 1 sig fig. If we go back and look at this concentration, that was our least, wasn't it? So we could have called it 2 and we could have been done with that. But we'll go ahead and keep that. All right, so where were you supposed to have ended? Well, I don't know that I gave you an end point necessarily. I want you to make sure that you get all the way through number 17. Now, some of you that just got your packet today, you have more questions than probably the rest of us do. So you're stopping at number 17 before you come back on Wednesday. I had another sheet that we were going to do, but I think you've got to finish that first. Yeah, so this is our lecture guide. This is not homework. This is our lecture guide. This is our lecture guide, sir. Yeah. Okay, guys and ladies, what you do need, we need some graph paper real quick. Let's see. Yes, we do. So let me see if I can. We're going to be sketching some titration curves. So, okay, so on the first graph that we're going to be sketching, we're going to be labeling our y-axis with pH, and our x-axis is going to be volume of strong base added, or volume of, and I didn't do a very good job with that, NaOH added. Give yourself some room because I did not give myself room to write numbers. Okay. I know. I'm not ready to make the scale yet because over here on the side would be pH. Now with pH, obviously we can make a scale because we know it goes from 0 to 14 generally. Okay, so we could start that one off. That could be pretty straightforward. 1, 2, 3, 4, 5. Yeah. 1, 2, 3, 4. Okay. Now with the volume, because we don't really know what our first number is going to be, well, I guess our first one's going to be 0. We're not going to add any. And then we're going to bump it up. So we can kind of look at this first piece of information. So on B, it looks like we're going to add 10 milliliters. And then on C, we're going to add 20 milliliters, 50 milliliters. So it looks like maybe we could, every 10, we could make a mark. But I would probably spread that out. Let's look at our total. Our total volume that we'll end up adding is 200 milliliters. So make your scale appropriately from 0 to 200. Okay, I've got to think about how I want to make mine.
How many marks do you have?
That's a good question. There's 5, 10. Yeah, I feel like I could definitely, every one could be 10 on mine. You have to go to 200 is your top end.
We need to go to 200.
Uh-huh. Okay, so this would be 200, I believe. We've got 50. This one's 100, 150, and 200. There we go. Okay, I'm going to name mine because we're going to be titrating a strong acid with a strong base. So this is going to be a strong acid, strong base titration curve. Okay, when you get your scale made and your title put on there, set that over to the side because we've got to start doing some work. Okay, we've got to get some numbers on here.
So what do we do?
Okay, so look at your strong acid, strong base titration. This is going to be sample exercise 1. It says we will illustrate the calculations involved in a strong acid / strong base titration by considering the titration of 50 milliliters of a 0.2 molar nitric acid solution with 0.1 molar sodium hydroxide. So for those of you that have not done a titration before, let me give you a little illustration here. In our Erlenmeyer flask, we will start off with some nitric acid. And we know the concentration of the nitric acid. We normally don't. It's usually the other way around. Okay, so we're going to titrate 0.200 molarity of HNO3. And the volume of our nitric acid is, we started off with 50 milliliters. Now, we have this really long tube. Can y'all remember, those of you that used this last year? What is that thing called?
Yeah.
A burette, that's right. Okay, and so it has this little turn thing that you turn and you allow some of the base, which happens to be sodium hydroxide, to be added into the acid. That's right. Okay, and we actually know the concentration of the base. So what we're going to do, though, is we're going to come up with a pH of what's going on inside the flask. And a lot of times, if you want to kind of give yourself an eye point, you will also add an indicator to your flask. Okay, that indicator will turn colors whenever you get close to the end point of the titration. And the ultimate goal of a titration is you want the end point to be your equivalence point. And what is the equivalence point? Well, the equivalence point is when acid equals base. When moles of acid equals moles of base. That's called the equivalence point. Okay? And if we have a strong system, if you've got equal moles of acid and equal moles of base, then the pH at the equivalence point is going to be 7, because you're going to have a complete neutralization reaction at that point. Okay? Then you can keep titrating past the equivalence point to continue your curve, but we're going to see some specific places on our titration curve. So let's start off with what we've been given, and then it says in A, no sodium hydroxide has been added. Now, if you want to calculate the pH for this, you haven't added any sodium hydroxide, so we're going to put our little pH probe down into our Erlenmeyer flask, and we're measuring the pH of this solution, right? That's a strong solution. Do we need a Ka for that? No. We just simply need to take the negative log of the concentration. Okay? So none has been added. Take the negative log of the concentration of the acid, because that's all that's in the flask. And so 0.200, 0.6989, 699. Close enough to call it 0.7, I guess. Okay, so on our curve, at 0 added, then our pH is approximately 0.7. Okay, so I'm about right in here, I guess. Close enough. Okay, one done. Now, we are going to start adding some base. And so when you add base to acid, you have a neutralization reaction. Let's just kind of write out. We don't have to write this out every single time, but I want you to think about what's happening. It's just a double displacement reaction. So Na and H are going to swap out places, and you have some sodium nitrate that is in solution. It doesn't actually form, and some water. Okay. Now, how much of each one do we have left? Well, we started off with 10 milliliters of a 0.1 molar sodium hydroxide solution. So let's work in millimoles. It'll make things a lot faster. 10 times 0.1 is what? 1. So we have 1 millimole of base. Now go back and let's look at how many millimoles of acid we have. We have 50, right? Milliliters. 50 times 0.2 is what? 50 times 0.2. Isn't that 10? So we have 10 millimoles of acid. Which one is going to get all used up? The base. So minus 1, we have none left. Minus 1, we have 9 millimoles of acid left over. Okay. Now, because I want us to practice this, we also make a salt, but this salt is a neutral salt because its pieces come from a strong base and a strong acid, right? There will be a point where your salt is not neutral, and so you'll have to actually use the Henderson-Hasselbalch equation to figure that out. But so since we're kind of practicing this, originally we have none of that. We made 1 millimole of it, but it's not going to affect our pH. Okay, so we won't use it in the pH calculation. All right, so we have just strong acid left. And how much do we have left? We know we have 9 millimoles. But whenever we plug in a number into the pH equation, what is that number always, what unit is that number always in? Molarity, right? Molarity. So we need to take this millimoles and change it into molarity. I'm going to take 9 millimoles and divide it by the total volume. How much volume do I have in the flask right now? 60 milliliters. That's right. 50 is original plus 10 sodium hydroxide added. So 60 milliliters. And 9 divided by 60 is 0.15. Okay. And then take the negative log of that to find your pH. Milli gets to cancel out. Because milli and milli cancel out. See how that works? Isn't that cool? That's why we can save time with putting things in there. We're finding the pH, right? Okay, so 0.82. So on our graph, we have now added 10. So go over to 10 and up to 0.82. So it didn't really go up much, did it? Kind of almost in the same place on mine. All right, let's do this again. Okay, so now we're going to add 20, the same thing. Okay, so we have 2 millimoles of base. I'm just going to do base, acid, salt. How about that? Okay. How much acid? We always start with the original amount, so we'll say 10 millimoles. 0 salt. Okay, so all that's going to go minus 2 would be 8 plus 2. We don't care though. So right now we have 8 millimoles of acid. 8 divided by your total volume. It's our total volume. We had 50 plus 20 would be 70. Okay.
How did we gain 20?
We added 20. Yeah. Yeah. So always think you originally had 50. Now you've added a total of 20 milliliters. Okay. So I got 0.11. Take the negative log of that because that's your concentration of your acid. And what did you get? 0.94. So we're not really increasing much at all, are we?
Yeah.
Say again. 8 was how many millimoles you had, and 70 was your total volume in milliliters. Yes. Okay, so that gives you molarity. That's right, and that's what we always plug into the pH equation. All right, so it depends on how you punched it in your calculator. If you did not use the rounded, if you use the number we wrote down on our paper, I agree, it's 0.96. If you use the number that your calculator gave you, you got 0.94. So would you guys agree that it's probably not going to make much of a difference on our graph here?
No.
All right, that's okay. So we're just going up. We're almost to 1, but not quite there. Okay, 20 milliliters added. All right, can you guys do the next one by yourselves? No problem. Okay. 5 millimoles of base. I'm not saying anything. I'm only putting down what I hear people say. How about that? How do you know which part?
Why does it matter?
It's always 10. Like that's your original amount that you started with.
How much salt we have to do?
No, not right now. We don't. But we're doing this just because you will. Okay. Strong. You don't care about the salt. No, it's just you had 50 milliliters of a 0.2 molar solution. Multiply 50 times 0.2. What are you going to get? 10. So that's how many millimoles of acid you started with. It all depends on what you start with in the problem. Okay. So
does that mean we have to go to 50?
Wait, what do you do?
Or volume in our graph?
okay. So how many do you have? What's your pH now?
1.3. Yes.
1.3.
Made it over 1.
Okay. So pH is 1.3. And we added 50 milliliters, right? That's okay. So 1.3. Looks like right about in there, something like that. That's where yours is too? Okay. Okay, Eli, question? Okay. All right. We okay? Okay, now we're making a huge jump. We're not doing this incrementally. You had 50 milliliters of base added to 50 milliliters of acid. Right. 5 is your millimoles, and 100 is your milliliters. Okay, how many? 50 plus 50. Okay, you have 50 base added to 50 acid. So think about this, Cab. You're looking for total volume in the flask. Okay, you're adding from the burette into the flask. Okay, so now we have 100 that is of the base. Okay, good. Your total volume is 150, Jamari. Good job. Okay. So the base this time, 100 times 0.1 is 10 millimoles. How much acid do you have? 10. Uh-oh. And the salt actually is going to be a neutral salt. So what did you say, Eli? It's going to be 7. That's right. Because it's all about what makes the pH neutral. Water. Water's the only thing driving the pH right now. Okay, so 0 of this. You do have 10 millimoles of salt, but that's a neutral salt because it came from each piece came from a strong acid and a strong base. Okay, so pH is 7, and that was 150. Wow, we made this huge jump.
Can we show that on the equation?
So basically, this is what's going to happen. I'm going to kind of show you how to sketch this. That was a total 150.
You're doing volume.
You're right. Thank you. This is not. You're exactly right. Thank you. My bad. Is yeah, on the graph I did the wrong thing. Yes.
Can you show that like on like equationally, like you prove it? That like negative log equals.
Oh yeah, you want me to finish this out? Sure. Okay, so the only thing that's here that's going to, we have no base, no acid left. The salt doesn't interact with water. The salt was sodium nitrate. Neither one of those are going to hydrolyze water. Okay, so the only thing that's left is water that is going to affect the pH. Okay. All right. So now F, we have 150 milliliters of 0.1 molar solution of base. So base, how many millimoles do we have? 15. Acid, we still go back with that original 10.
Can I have your attention, please? At the beginning of fourth period, I need the following students to report to the front office. Kylan Allison, Jerome Hopper, Cody Hughes, Tara Johnson, Chandler Langstaff, Amari Perry, William Malden, and Andrew Smith. At the beginning of fourth period, please report to the office.
Okay, so we have 5 over 200 now, right? Go with me on that part? I just plugged it in there. Right. And it's all about the base. So when we take the negative log of that, that's not pH, that's POH, because that's about the base. Okay. Yeah, I just went ahead and threw it in there. Subtract from 14, you got it. So 14 minus that is going to give you your pH. Jasmine? You're adding 150 milliliters to your original 50. So your volume in your flask is 200. Okay? And remember, that's what this part is. This is millimoles divided by milliliters. Okay? So that's concentration right there. It's moles per liter. After you subtract, okay? So total of, what was your POH? 1.6. Okay. And so 12.40 would be our pH. And that's at 150 milliliters. Yeah, we have to be careful with that. Okay, so at 150 milliliters, we're all the way up to 12.4. I can't. This is hard for somebody with astigmatism. I need a ruler. Okay. I think you're right. You should always put your units underneath that. So volume of NaOH added, milliliters. Excellent work, Casey. Okay. Now we have one more, and let's see what that is. Okay, so we have 200 milliliters. So base, we're starting out with 20 millimoles. Acid, we have 10. Salt, 0. So minus 10, we have 10 left. Minus 10, 0. Plus 10, 10, but we don't care at this point. Okay. So this time 10 divided by 250, good.
0.04.
And we take the negative log of that. Remember, that's going to be POH. And then you'll need to subtract 14 minus that. POH gives you your pH. So what'd you get, Javante? 12.6 for your pH. Okay, and that means that your POH was 1.4. Okay. All right. Yeah, don't draw anything on it yet because we are missing a whole bunch of curves, but go ahead and put your last point on. And 12.6 for a total of 200. So it pretty much flatlined there.
Where did my pencil go?
I don't know. Did you just lose it? Okay, so it looks like it kind of looks like it might be an S, but I want you to see what all those missing points that we didn't put a point for. If we had point, let me show you what you would have gotten for a strong, let's try it again. Strong acid, strong base. Actually, I want to go strong base.
Wait, what's the pH for?
I want to reverse this. Okay, y'all ready to see what it's going to look like so you can connect the dots? Strong acid, strong base titration looks like this. Okay, so all those that little blue area, if you're close enough, you can see those are actually points, data points that we're taking. There's one data point right here. Okay, with a strong acid, strong base, the equivalence point is hit quickly. Okay, so you increase. So on yours, notice that where your equivalence point is at 7, okay, I want you to basically see where it starts. Yours starts curving up. Let me go back to this so I can show you what I'm doing. Okay, so where your equivalence point is, kind of drop a line down, make your line go up, because we're going to make this little S curve. So we're going to increase, boom, and then we're going to come over here and do this. Something like that. I didn't do a great job, but that's the general idea of what a strong acid, strong base titration curve looks like. So on that picture or that graph that we had an example of, they had data points all through here. And then all of a sudden, they hit right there, and their pH shot up. In fact, it will shoot from, it's like you add they might have taken it. If they were good, they got a data point there. But most of the time, you end up with a really low pH, and then boom, as you're doing this titration, you're way up here. And then you get all these other data points across here, okay? All right, so that's what a strong acid, strong base titration curve looks like. Say again. So it's at neutral. It's neutralized right here. Oh, it's hard to get neutral. Yeah, it really is. Because if you do, I mean, you're a great titrator or you're lucky. One or the other. That's exactly right. So we can look at that real quick. Casey's like, what is a strong base, strong acid? So I'm going to reverse this, okay? So Casey's predicted what it looks like. If you start out with a strong base, you would start with a high pH, right? Where would your equivalence point be? Still be at 7, and then you would end low. So when we titrate that, notice it's exactly it's like a mirror image almost, okay? Or is it? It's not that way. It's like flipped, yeah. If you turn your paper over and you can see through it, like flip it upside down, you can see a strong acid, strong base, a strong base, strong acid titration curve. You can't see through yours? Okay, I can see through mine.
Oh, there you go.
Yeah, hold it up to the light. There it is. So if you can see through it and you want to label the back of it, you can label it if you wanted to, okay? All right, now let's look at, this is actually the titration. If you were in my class last year, we did a strong acid, strong base titration, okay? We did. It was fun. Okay, so we are going to now move on to the weak systems, because the weak systems it's all about, we're going to have to look at the salt. You got it. Good, Casey. Are we going to do a lab? We can actually probably do one this week if we get through titrations pretty quickly. We can do a titration lab.
I thought we were going to do that lab.
The buffer lab, we were supposed to do a buffer lab too. Well, actually in a titration lab, you'll end up having a buffer system created. So may be able to do both. Okay. So let's make sure we understand the basics of titrations, and then yes, we can definitely do a lab. Okay, let's look at titration of a weak acid and a strong base. So we've got more than one piece of paper, I do believe. I hope. If not,
Putting it on the back.
you put it on the back. So we're going to go ahead and set up our curve the same way. We want pH. on the y-axis, and on the x-axis, we want volume of, what strong base are we using? We're using sodium hydroxide again. I'm going to give mine some room, though. All right. Because I forgot to do that last time. Hey, Miss Macon. How are you? Good. There you go. Casey, she's right here. Okay, make sure you label pH, and pH doesn't have units, so we don't have to put that. And then our title for this one is titration, or weak acid strong base titration. So any way you want to name that, I'm going to call mine WASB titration. What I put where? On the bottom? Volume of sodium hydroxide added, and that's in milliliters. Caleb, don't make me call you out on the video.
Oh, I'm just dead. You remember how you're going to Caleb? I want to get up there.
Say again. Oh, I typed. This is a weak acid strong base titration. Okay. So, yes, ma'am.
On the bottom part, it's just what you add to it. It doesn't
Right.
have to be a base. It's just whatever you're adding.
Right. It's whatever you're adding to it.
Well,
Yeah.
we don't go over.
On
Well,
this
actually,
one.
I take it back. Never mind.
Ooh, we stopped at 75,
Yeah,
didn't we?
Mhm.
Or did we? Does this continue on? No, it does not. So
50
maybe ours,
goes
we're going to have a
over.
little skewed. In fact, I may redo my numbers. I don't know.
125.
Oh, but it's how much is added, though.
Yeah, 50
So-
plus 1. 50 plus 75.
That's a total. But on the x-axis, this is how much is added, not total volume. Sure. Pass that to Cab. Anybody wants to use the whiteout, don't just tear it up. I'm not thinking you guys will, but
So what would be the
sometimes
max?
people don't know how to use it and they start pulling stuff out.
Oh, you know you're going to do extra 60K.
Yeah. So say that again.
So
How
what will the max be for volume added?
the max added, it looks like it goes to 75. So I'm going to do 25, 50, 75, 100, just because I had 4 places there. That way everything can be at 5, 10, 15, 20. Like each one of my little tick marks can be 5. But you guys do the way you want to do yours. Just remember, if you don't spread it out, it'll just be kind of scrunched up. Okay. Scrunched. Okay. Let's look at, do I have all this extra writing on yours? I'm not real sure why. Okay. All right, but let's look at what we've got. We've got 50 milliliters of a 0.1 molar acetic acid solution. And here's how we know that that is a weak acid. It's got a Ka value, right? So as soon as you see that, it's like, okay, it's a weak system. They don't give you one unless they're asking you to calculate the Ka value. They should give you enough information to be able to do that, okay? So always think about, what information do I have in order to work this problem? There is enough information here. All of these problems are workable. You just have to figure out the puzzle and figure out what you know to be able to work out the puzzle. The puzzle pieces are there. Your job is to put them together. Once you realize that, you'll be like, yeah, I can work any of these. It's a puzzle. That's right. That's right. Okay, so here we've got we're titrating this acid with some sodium hydroxide. So which part is in the flask and which part is in the burette? Is the acid in the flask? Okay, so which one is in the burette? The base is in the burette, yeah. How do you know? Look at what you're adding.
Whatever's added is in the
Whatever's added is in the burette, yes. Okay, so this part is in the flask. What else would we put in the flask with that acid? I told you a few minutes ago. An indicator, very good, okay? And that indicator will turn colors whenever you get close to your equivalence point, if you have chosen the correct indicator. All right, this is in the burette, B-U-R-E-T, or some spellings B-U-R-E-T-T-E, actually, yes. Okay, all right, we've got our acid, 50 times 0.1, so how many millimoles do we have? 5. That'll be crucial in a second, but we haven't even added any base, so it's just about the acid right now. If I need to find the pH of this, I'm going to need to use my Ka expression. So Ka is equal to H plus times C2H3O2 minus over, very good, close brackets. Okay, so now Ka is, I could use the Henderson-Hasselbalch if I wanted to, but to me, whenever this is not a buffered system, I like to just go back to this. The Ka is 1.8 times 10 to the negative 5th. What's going to go on top? Do we know those numbers? X, but X squared, good, divided by the concentration, 0.10. And we get to neglect X because those two numbers, what two numbers? Ka and this one are 1,000 times different. That's right. Okay, so let's solve for our X. Remember that our X is equal to the hydronium, and then we'll take the negative log to find pH.
Why are we doing negative log to find the
pH, that's what they added. They asked for us.
Why can't we do, since no base has been added, why can't we do the Hasselbalch with PK?
You could have.
Plus.
You could have done it either way.
Log would have been 0. But we're adding no base to it. It's going to be
True. Well, I think the Henderson-Hasselbalch would have been harder to use because think about your parts in the Henderson-Hasselbalch equation. You don't know two parts, so that would have been difficult to deal with. Okay, only use the Henderson-Hasselbalch when you don't know one thing, the pH. And this time we don't know X, and so we had to find X. All right, so Javante, what X value did you get? Okay. All right, so that's our X value. 1, 3. Let's go ahead and take it. No, I like 1, 3. Okay, so pH is 2 point, say that again, Casey. 8.9. So let's go with that. Well, if it's 2.87, it still would end up being rounding up to 2 point. Right, if you put your entire number that you had in your calculator. So if I take the negative log of that, yeah, 2.87. Yeah. Okay, so let's flip this. Go ahead. Okay, so on your graph, if you are there, go ahead and you're at 0, and your pH is starting off already higher than the other one, isn't it? Yeah. .89. My point looks a little skewed there because I look like I almost put it at 3, but we get the general idea here. Okay, let's move on. Okay, so now we're adding some base to our acid, and we're going to make a salt. Okay, our salt will matter this time because we have a weak acid, and the conjugate of a weak acid is stronger than water, exactly, which means that it's going to also affect the pH. Okay, so let's find out millimoles of base. We have 10 times 0.1, that'd be 1, right? Acid, we have 50 times 0.1, which is 5. So the base is all gone. The acid, we still have 4 millimoles of that. And our salt, we have 1 millimole of our salt. Okay, so this would be an excellent time to use your Henderson-Hasselbalch equation to do pH. Because you've got, Alex, you're overstretching there. You've got both conjugate, base, and acid, right? And so in the Henderson-Hasselbalch equation, you guys find the pKa real quick of that acid. That way we can use it every time. You take the negative log of 1.8 times 10 to the negative fifth. Okay. All right. Go back right here. 4.74. Okay. So, Tyler, take the negative log of your Ka value. Okay. That's how you get pKa. All right. That's not pH. That's pKa. I hadn't finished writing the equation. All right. And then plus the log of base over acid. So, the salt is what part has the base in it, right? When we're talking about bases, we actually have 2 different bases that we're dealing with. This is the base that is the strong base. The salt has the conjugate base in it. So we have 1/4. With the Henderson-Hasselbalch equation, because this is a ratio, you don't have to recalculate your concentrations on this one. You can just put your millimoles in there.
Okay. So I'll
The bottom number is going to be how much acid you have left over.
okay. So that's the
Hey,
same.
Alex, you got a pen on that?
Right. But we have acid left. Okay, gotcha. Yeah. Well, we'll talk about that. We gotta talk about that. Okay. All right. So what are you guys getting for your pH now? 4.14. All right.
So our salt is the base.
So our salt is the conjugate base. That's right.
Oh,
Yeah. Okay. So we just added how much? 10. And we're going to 4.14. No, because, you can. This is just a shortcut way of doing it. If you use the Henderson-Hasselbalch, realizing that it could be molarity over molarity, which would cancel out, or you can put moles over moles or millimoles over millimoles. Okay, either way, so we'll just save ourselves some times. Oh, on the graph, no, that's not total. That's how much is added. All right, let's go ahead and let's get the next one in. I think it's time for you guys to do this one without me. You can tell me what to do, and I'll put it up here on the board, but I think you're ready for your own. Jasmine? Okay, so I'm going to put strong base plus acid yields. And instead of us calling that salt to keep our mind straight, let's call it conjugate base. Okay, so how much strong base do we have to begin with? 2.5. How much acid do we have? 5. How much conjugate base do we have? Okay, which one's going to go away? Okay, now our pH is equal to the pKa, which is still 4.74. What do you get when you do the log of 1?
Words. PK.
Yeah.
Because the log of 1 is 0, right? So then pH is equal to the pKa. Now, this is a very special point in your titration. Okay, let's make a big deal out of this.
Do I put a star next to it or something?
Yes, put a star next to it. Okay, you've added 25 milliliters to your solution. Notice that your acid and its conjugate are exactly the same. Okay, you're at the halfway to the equivalence point. You're halfway to where you would, your end point would be reached. Okay, so let's call this halfway to, there you go, exactly. You're at the, so if you knew you're halfway to the equivalence point, then you would know where your equivalence point was. Very good, good observation. Halfway to the equivalence point, pH equals pKa. That's just a little factoid. At halfway to the equivalence point. At the halfway to the equivalence point, pH equals pKa. Say that again?
Yes.
No, it's not going to be 7 at the equivalence point. Okay, we'll see why. Okay. All right, so now we just added, do you need me to move that, Jamari, before I put my thing up here? Okay. All right, so 25 mils, and our pKa was 4.74. And so we haven't made it to 5. Here we are, right there. Look at that. It's kind of curving, isn't it? Interesting. Okay, a little bit of a curve. We didn't have that little bit of a curve on the last graph, did we? It just kind of went straight. But this one has a little tail right now.
The other one has a little curve towards the equivalent.
Exactly, exactly. Okay, let's move on. And I'm not trying to slow us down. Okay. Strong base plus acid makes conjugate base. All right, how much strong base do we have now? 4. Acid originally 5. Okay, conjugate base 0, so all the strong base is gone. 1 millimole of the acid and 4 millimoles of the base. So this one looks just like B, except the log part is flipped, isn't it? So pH equals 4.74 plus the log of 4/1. Okay, so the pH is what? 5.34. I thought you said 12. It was like kind of scary there. All right, pH of 5.34. We're going up, and that's at 40 added. All right, 40, and we're at 5.34. I think so. Yeah, it is. You're right, because we already found our halfway to the equivalence point at 25. So 50 has to be our equivalence point. Okay, so strong base plus acid goes to conjugate base. So our strong base this time we have 5. Our acid we had 5. Our conjugate base 0. So it's all gone. But we have some conjugate base. Yes, it does. That conjugate base has been affecting our pH, hasn't it? Okay, Alex, what are you?
But if you put in the like Henderson-Hasselbalch equation, if you put conjugate base over acid, then that would be 5/0, but you can't divide by 0.
So we're going to have to work this one a different way. Okay. All right. So now, would you guys agree that we have just conjugate base in here, right? And that conjugate base is a stronger base than water, which means our equivalence point will not be at 7. It's going to be a little bit above 7 because we have some conjugate base in there. So don't we need a KB for this conjugate base since it's a base? And when we plug into x squared over, now we do need the concentration of this. We have 5 millimoles. What's our total volume? 100. 100 is the total volume of everything in the flask. So 5 divided by 100 would be 0.05. Okay, so that's our concentration of our conjugate base, but we need a Kb. So Kw divided by Ka gives us our Kb. And you guys, we're going to assume this is at 25 degrees Celsius. So what's your Kw value? 1 times 10 to the negative 14th divided by your Ka of 1.8 times 10 to the negative 5th. And I got 5.56 times 10 to the negative 10. Okay? All right, so 5.56 times 10 to the negative 10th equals x squared over 0.05. All right, you guys, when you solve for x right now, what is that going to give you that's going to allow us to calculate pH? Is that going to give you H plus? No, that's going to give you OH minus, because this is a base. Right, good. Take the square root of that. And it should be times 10 to the negative 11. Eli, you didn't multiply your 5.56 times 10 to the negative 10th by 0.05. Yeah. So this should be. I think we need the 2 for sure. 2. So it's 5.27. Okay. Oh, you asked decimal places, and I meant sig figs, but it'll be fine. I'm just going to take it out of my calculator. So, what went up? Yeah, it did.
Like, just a while ago, it was like right here.
Yeah? No. Probably warmed up a little bit in the room. Probably from this heat from the lamp a little bit. Because the pressure, gas pressure is dependent upon temperature, too. Yeah. All right, so negative log of this. And I got, that's not right. Oh, 5.27? Is that what I got? Okay, so that's POH, right?
Wait, what did you do to get negative log?
Yeah. And then our pH would be 8.72. How you doing, Cab? Okay. 60. Okay, so we have recognized, hopefully, that we have reached the equivalence point at 8.72. Okay, make sure you mark that on your graph. And that's at 60, right? 60 is added? Or was that 50 added? That was 50 added. My gosh. My bad. I know. I need my whiteout back, though.
Oh.
Alex, can you grab that?
Yeah, whiteout.
Thank you. I was looking at the wrong thing. There we go. Okay. Nope, you aren't. It's going to get easier. I'll show you. All right, so now, guys, the rest of this, once you hit the equivalence point, the rest of this is easy, okay? Because it's all about the strong base. Let's look at what we've got. We've got strong base plus acid makes conjugate base. So our strong base, we have 6 millimoles, the acid 5, conjugate base 0, minus 5 would give us 1, minus 5 would give us 0, plus 5 would give us 5. But we've got a situation if somebody's going to win this battle. We have a strong base and we have a conjugate base. Who's stronger? The strong base is stronger. So even though we have 5 millimoles of that conjugate base, it is so much weaker than the strong base that we're titrating with that it will not affect the pH, okay? This is the thing that's going to affect the pH, and you can be happy about that because once you get past the equivalence point, it's a really easy problem to work. All right. We do have 1 millimole of this. And what's our total volume that we just added so we can get concentration? So yes, 110. And let's find our concentration of our strong base that's left over. 1 divided by 110. Okay, so 0.009. I'm going to go ahead and call that a 1. And then because that's a strong system, we don't have to do Henderson-Hasselbalch. We don't have to do x squared. Excuse me. Just take the negative log of that. That's going to give you POH, because that's a base. And then subtract that from 14. Okay, so now 60 mils was added, and we're way, way up here, 11.96, almost to a 12. Can't really tell where I'm at. Okay, there we go. Okay, last point. Now,
That was easier.
yeah, it's way easier. Once you get past, like I said before, once you get past that equivalence point, you are in home stretch. Okay, so strong base, we have 7.5, acid 5, conjugate 0. It's like we're keeping a scoreboard here. -5 would be 0, +5 is 5. We don't care though, because it's not going to win out over the strong base. So I got 2.5. Make sure I did my math right there. And then I'm going to need the concentration, so 2.5 millimoles divided by the total volume, 125. And then we're going to need to take the negative log of that and subtract from 14. There we go. Sorry. It's like, that seems odd. 1.7. Okay. And 14 minus that, 12.3. All right, so put it on to our little paper, and that's at 75, 12.3. Absolutely. Sorry, I just needed it to be there so my paper wouldn't fall down, but
We can do this after the equivalent point, just not before.
not before. So let's do some marking on our little curve though, okay? First of all, do you want to see like I guess a better graph with all of the points on it? Okay, so this is we titrated with a, let me reverse it, strong acid and a weak base. Is that what we did? No, we didn't. We did weak acid, strong base. Let me find one. That's not it. Strong, strong. We did weak acid, strong base. Weak base, strong acid, weak base. Is this the right one?
Weak acid, strong base.
It's not the same thing. Okay, give me a second. I'll find it. Nope. Do you see it? Titration.
How many times do you think you get on that one?
Enough to make September really irritated with me.
You know that's 27 right there.
I don't think so. Is it really?
Count.
Let me find where I found this. Titration checkpoint examples. I think that's it. That's not it. Okay, I'm closing it. I'm trying to find.
29. You count it?
All right,
My bad.
that's not it. I'm gonna close this one. Hey, does that make y'all feel better? I'm also gonna close this one. Oh, look at that. Yes, it's gonna look like that. Yes. I was trying to see if I could find one, but there is not. It's weak base, strong acid, which is gonna look like that. So yours is gonna look like the reverse of that. Why is that mislabeled? That's a strong acid, weak base titration. This should be, okay, that's still not right. Strong acid, weak base. They've got that reversed. Okay, let's reverse this. I want you to see. Now, yours will be the mirror, the flip image of that one. Okay, so let's go back and let's draw points. Now, we're going to include this little tail right here. Notice that's a curved area. And on this one, honestly, you can just kind of connect the dots. No, it actually slants. It's more of a slanted area, or it may be whenever it's straight, it may be like here to here, but it's not very long, okay? So if you wanted to kind of straighten that out, you could. Okay, so let's mark some things on our titration curve. Okay, what is this point called? That's the equivalence point. Okay, and then at 25, like Casey said, this is the halfway to equivalence point. And what was so special about that?
Oh, what was that?
The 25 was our halfway to the equivalence point. That's where pH equals pKa. Okay, now at the equivalence point, what do we have to deal with at the equivalence point? Instead of a Ka, you had to have a Kb. It's a Kb calculation. What about after the equivalence point? None of that. So after the equivalence point, this area, in fact, if you wanted to shade it or something like that, this was an easy calculation. All about the strong. So if you know some information about your titration curve, then you can figure out some of these problems without having to stress yourself out. Okay, so it's all about the strong. At that point, the equivalence point is a Kb problem. And the halfway to the equivalence point is where pH equals pKa. All right. And then if you don't have any base added at 0 point, that's where you're going to deal with just a Ka. That's a Ka problem. Okay. Now, the cool thing about to the equivalence point all the way until you get right to the equivalence point, this area, you're in buffer land. So you can use the Henderson-Hasselbalch equation. Well, it was pink, and it looks very colorful over here on my paper, but apparently it doesn't look very colorful up there. Yeah. All right, so you're in buffer land. This is a reddish color. I know.
That
Yeah.
is so weird.
I know. I know. Mine is all colorful up here. Sorry, you can't. Yeah. All right, buffer land, halfway to the equivalence point, pH equals pKa.
You can't see the green.
You can't see my green? My little, here, see?
Oh, a little bit.
It's
Bro,
a little.
it's like, is this is probably what my dad
No,
said.
he was saying my fingernails. I have little clovers on because, yeah, they're green. Well, all right, guys and ladies, we're going to I think we get the idea on the next titration curve. So let's go to your buffer packet that you were working on, although not all of you have that, do you? Dang it. We need some more stuff. Actually, why don't we do this?
Yeah.
Let's go to buffer packet, but not everybody has the same, not everybody has the back pages. So let me look at this. I'm either going to need to go run y'all some copies of this thing or I think our buffer packet. There are two different things.
Can you check the file?
So September, did I give y'all something else to pick up? No? Okay. All right. Let me go run some stuff real quick then. Okay? You guys be real patient with me. September, let me see your buffer packet. Yeah, the one I just gave you. Okay. Because not everybody has the extra pages on it. Yeah, see those? Extra pages. So, here's part. Or do y'all? Do y'all have extra pages? You do. Hey guys, look at your buffer packet, this big thing that we were working on last week. What's the last page that you have? Look at the very bottom,
2015.
right-hand corner. 2015 question 3.
Yeah,
Okay.
17.
Not bad. Then you have enough. Okay, so let's go to page 12 in our buffer packet. Numbers are very tiny. Page 12. Okay, let's look at this titration curve that they give us here. Okay, page 12. Do you have a page 12? See, I knew some people didn't have page 12. Did you? You should have a page 12 then. But if you don't have a page 12, then we will get you a page 12. Wyatt, come switch with me. Then I'm going to, never mind. I'm just going to go run y'all copies of this. How about that? How many of you need a page 12? Raise your hand, please. 1, 2, 3. Is that it? Everybody else has a page 12. The new copy doesn't have a page 12. Okay, so right now, those of you that have a page 12, I want you to go ahead and answer question A. So show the chemical reaction that occurs to result in a buffer solution when 20 milliliters of sodium hydroxide has been added. So you're adding sodium hydroxide plus HNO2. Okay, go ahead and do that while I go run off 3 more pages of the rest of this. Start off with adding your acid. Oh.
Kev, how much did you get for the base and acid?
How much did I get paid?
And acid. Did you get 1 for acid and 0.2 for the base? I'm talking about 18A.
Yeah, just write the reaction. This is 3AB. You should be able to write that reaction. Is there anybody else who didn't have that page? You have your reaction written? You didn't call on you? Okay, good. What do you have? All right. You're waiting. Okay. I got these all out of order. Okay, so Alex says that she has NaOH plus HNO2. Alex, tell me the rest. Okay, so what is NaOH? That's your what? And is it the strong base? And HNO2 is the, and NaNO2 is your salt, which has your conjugate base in it. Very good. That's right. Good. Okay. All right. Using the curve, determine the Ka value. Now, how did we, there's a special place on this curve which can help us know the Ka value. What are we going to do? The halfway to the equivalence point. So find your equivalence point, which looks like it's about at 100, doesn't it? Maybe. Here, I'm going to try dropping that down better. So at 50 is your halfway. What's your pH at 50? 3.5. So 3.5 is your pKa. How do you find your Ka?
No,
Antilog of a negative 3.5. Times 10 to the negative 4. There you go. Then it says, show the buffer calculation that relates to this determination. Well, then we could use our Henderson-Hasselbalch, right? Huh?
Oh, do we get that from the graph or something?
Yeah, at the halfway to the equivalence point. Okay, so you find your equivalence point, which is at 100. At the halfway point, a half of 100 is 50. This is where pH equals pKa. Okay? So now that we know those two special places on our graph, then because we know that here we're about to show it, okay, because it says show the buffer calculation that relates to this determination. Okay, so if you use your Henderson-Hasselbalch equation, pH equals pKa plus the log of what? Base over acid. Okay, now at the halfway to the equivalence point, what parts are equal?
pH and pKa.
pH is equal to pKa. Why? Because the base and the acid have the same concentration or the same number of moles. That is correct. Because the log of 1 is going to be 0, which is going to mean that these two things are equal. So at the halfway to the equivalence point, conjugate base equals acid at that point. So you could call both of them the log of 1, okay, which is going to be 0. Well, I'll need a plus sign there, sorry. I'm just kind of writing my equation here. Backwards.
Oh, okay, I see what you mean.
Now, there we go. Sorry. I was talking it through and then I was getting there. Yeah. Okay. Now, C, use one color highlighter or pen. Trace the values on the curve for where HNO2 is greater than NO2 minus. So where is it greater than? Where is the acid greater than the conjugate base? Well, where do we stop? No, it's not just where it's lower than 7. It's right there. They're equal, aren't they? And so once you pass that equal point, then what happens to them? Who's bigger? The base is bigger than the acid. Okay, so this point from there to there is where HNO2 is greater than NO2 minus. Now my color is not going to be the same. I'm going to use something else. At this point, all the way up to here, to the equivalence point pretty much, that's where NO2 minus is greater than HNO2. All right, you've just done number 18. So your job tonight is to do number 19 and the reflection questions.
How did you get
Okay.
3.16 times 2 negative?
Take the anti-log of a negative 3.5.
Okay.
Okay.
Bye.
You too, Alex. Thank you. That sounded a little like, have a good day. Like, it's okay. No, it's like, are you frustrated?